this. Okay, so this is lecture number 10. We are going to discuss components and composition. Mainly, we will talk about the decomposition of the matrix method. Okay, so it's widely used in many fields in machine learning and also in the biology-related study. So we will generally cover the concept of matrix decomposition, or it's called matrix factorization. And then we will go through non-negative matrix factorization, NMF, and then Eigen decomposition and SVD. At the very end, we mention this ICA. They all matrix decomposition methods. So Eigen decomposition and SVD has long history, and NMF is a relatively young algorithm or method. So I put this upside down to introduce the younger method because it's more relevant for to biology, okay? Because most of the biology measurement get a positive or non-negative value. And also it's more intuitively sound and easy to understand in general, rather than the Eigen decomposition or SVD. So in linear algebra, matrix decomposition or factorization is a factorization of matrix into a product of multiple matrices. Normally, it will be 2 matrices or 3. There are many different methods to do this. So that's from the Wikipedia page, and you see a lot of those. There forms big families of different decomposition methods. So that's what we are going to do today. Okay, in lecture 2, number 2, I believe I introduced matrix multiplication using this example that's your roommate and you want to do the breakfast with a different ingredients, and to do this sandwich, you have to buy different numbers of those. So you have the concept of components. You want to make some sandwiches. There are different components you need to buy in order to make the types of sandwich you need. Okay, so in this example, I certainly use that to show you how to do the matrix multiplication, but you get the idea of composition. But now we are going to do the inverse. We want to have the end product of how many different components you will buy and your roommate will buy, and decompose this matrix. So inversely, can you just figure out what kind of sandwich, how many you want to make? So that's a reverse problem factorization rather than multiplication. So that's the whole idea. The many key ideas in linear algebra, when you look at them closely, they're really factorization of a matrix. Okay, original matrix would decompose into 3 or 2 spatial matrices. And there's meaning in those sub-matrices you want, not sub-matrices, but decomposed matrices. And sometimes you need to have your own interpretation if you really have that. This particular example is Netflix. Netflix give you play videos, movies, and the users will watch them and score in different scale and like it or not. So once you have this matrix, this user and the movie matrix R, normally it's a sparse matrix because there are very few data points actually have the information. you can decompose it, and there approximation sign in the middle to decompose it into two matrices. Okay, you have users and give different features of these user groups. You have a D components to describe them. And then same numbers of components you gave to movies. And because the internal matrix dimensionality matched, so D matched D, and you can do the multiplication between these two. And the end product of these two will be very numerically similar to your original R matrix. Okay, so that's approximation of that. And then the next, you will have to look at your components of D and see how you use D to classify users or classify movies into different subgroups. All right. So NMF is also right as sometimes as NNMF because it's a non-negative matrix factorization. This is a group of algorithms in linear algebra to factorize a given matrix. In this case, is a V and factorize into the product of W and H. Okay. So you can see in this example, this V input matrix was decomposed into W and H, highlighted in this, and the values indicated by the color, and the red indicated higher value, and the blue lower values. And so this shouldn't be equal sign because it's unlikely to be exactly the same. So it should be approximation. Okay, you approximate this by only use 3 components each. So you can see for this example, if you multiplicate this by that, you create some of those groups in the original data by learning from the data itself, like decompose and learn its structure. So the structure was encoded like here. You have 3 blocks. Okay, so if you have a very noise input data, you won't be able to directly see it, but if you have W decomposed components in there, then you probably can see it. So this is an abstract example, but in general, if you have gene and the cell matrix like this, you decompose it into components, and those components probably will be the gene expression program. They're co-expressed gene from a component, and also for different cells and how much each component contributed to its overall program activities of biology. As I said, NMF is a relatively newly developed method. But you see, at the first glance, it's nothing but just factorization method, okay? Similar as singular value decomposition. We will mention SVD later, or IDC. So there's nothing special. Why is developed so late in the history of methodology development? Well, it looks easy. And because of this constraint, you require all the elements in your decomposed matrix has to be non-negative. So this constraint actually make the computation even harder. Okay, and then people realize there are smarter ways to do the algorithm and then make it extraordinarily effective. So that's where the NMF become popular, and because the non-negative feature and make it applied to a wide range of the problems later. Okay, so because of the computational effectiveness, and then in the real life analysis, there's abundance of non-negative data, and that's why it sparked the substantial amount of research in many fields. And right now, if you open any machine learning or unsupervised machine learning method in biology, in gene expression analysis, you will often see NMF, different variations, types of the new creation of NMF, but it's under the same umbrella all the time. Okay. Okay, mathematically, if you express that, is you have input X matrix, and you want to approximate it by using the product of U and V. Here V is transposed with this transpose. Sorry, okay. So NMF, you actually run optimization under the hood. So you can have a matrix by M by N and decompose them into M by D, D by N. And you can put a random number in there first, just like unknown parameters, and make a product. Then you compare your product with the original, see how can you change the value in here and optimize, make the difference between these two matrices as smaller as possible. So that's the cost function of this NMF. I'm sure you have seen this. Okay, so you should be able to explain that right now. So that's a norm, right? And this is the difference between given is the input matrix V and the product of a W and H. So the difference is the errors in your estimation. You want to make this matrix level norm, this L2 norm for the matrix. To make this as smaller as possible. So that's your cost function. So you want to minimize this. Okay. In this case, I showed you before. If you have a problem, you can solve it. If you can create cost function or loss function, and you can plug in the general optimization engine, and this algorithm will compute the result for you. But in this case, we have too many unknown parameters here because every element in matrix W, in the matrix H, are supposed to be unknown. This is a little bit overwhelmed for the general optimization engine, and also there's non-negative constraint, make it probably a little bit harder. So NMF algorithm solve this by using iteration and to update the values by a loop, and each loop you compute the difference and recompute the values in there, and quickly you can get a converged solution. But eventually you're still based on this cost function, which square the error indicated by this L2 matrix norm or the Frobenius norm. And also you can have this KL divergence as your cost function. There's another way to write this. So you can do this way, or you can also do that way. KL divergence is compared to distributions. And if the two distributions are similar or identical, you have a very small norm D. And that's involves this log of ratio. Okay, so that's a way in the original paper proposed, and IMF authors propose using this KL divergence as a loss function. Okay, so you have so it depends on your selection and which cost function you will use. The minimization procedure a little bit different, but they all based on this iterative update rules. These rules defined in this here. Okay, so what's this rule here? This rule tells you this previous step you have H. Previous step you have W, so you can initialize by these two matrices using random number in there, and you will keep update by compute this term, and then do this element-based multiplication and update values in H and give to the next generation or next iteration. You keep updating until you reach to some criteria, then the loss function gives a value smaller than certain cutoff, and you stop. Okay, for divergence, for to norm, you minimize this, and for divergence, you normalize this. Okay, by giving this, and what's the distribution difference between them. Now I'm going to show you the iteration function inside this solution here. Okay, when you see this IK, because there's 2D matrices, they all, so that's indicated that's for every element inside a matrix, you update it. So you update the value of this by using the ratio between this product divided by that and give updation. And this is for V, this is for U. Okay. Okay, so here is a derivation of why this is the case. So here, the optimization, the derivation of optimization rule will be demonstrated, but I'm not going to go deeper because here you will have the derivative and the partial differentiation. You have to look at the change of this loss function. So here is loss function and the values, and then you have to set this equals to 0 and to find the solution of the updated rule to give you the minimized loss function. Okay, so just like last time we tried to derive this normal equation for gradient descent to find the solution for the regression coefficients, and you set this slope of this into 0, and then calculate analytical solution for beta value. Here is the same. So using this to work out why this keep updating will give you the minimized cost of function. Okay, so eventually, that's your loss function, the object you want to minimize, and that's the rules for updating. And if you do this, you will get, for example, if you have that, you will be able to decompose into this red matrix and the purple matrix. The product of this will be very similar, almost identical to your input matrix. So inside implementation of source code of MATLAB code for doing an MF, you can identify those updating parameter updating procedures. For example, here you can see, okay, I can find exactly copy basically the equation here in the MATLAB code here, and also for this implementation also found the similar solutions. Okay, for example, here you can use two different cost functions. If you use the norm, which Euclidean distance, you get the equation of this. If you use KL divergence, you have this cost function using this formula. But the update rule are this for Euclidean distance are this, which I just showed you in the previous slide. Okay, so that's inside the function, the source code. It looks like that. MATLAB machine learning statistics toolbox have this function in MF, and that's a description of this function. And you give input matrix A and get a matrix W and H, and it can specify how many components you have in the H and the W. Okay. So internally, this factor are chosen to minimize the root mean squared residual of D between A and W times H. Okay. And it also said the factorization use iterative method starting from a random initial values of H and the W, and then to iterate and minimize the difference. So any questions so far for this method? The principle underlined here. Similarly, this in the Python skit is a package also have this skitlearn decomposition method and their description similar in a similar way. Objective function is this where applications. So I can trace back a new an older paper as old as 2004 paper in PNAS. This researcher started to use NMF in gene expression and molecular pattern discovery applications. And the NMF method has become popular since 1999. And then it's only 5 years later and started to show up in biology literature. That's maybe we have early papers using the method, but that's one I can find, one of the earliest. So in this, they define some key term called meta gene. So basically, it's a composition of a similar gene grouped together. They kind of meta gene. And then for this observed matrix, you have a number of genes and number of samples. You decompose them into meta genes. So all the genes behave similarly, will be grouped together. So there's only 2 classes to be found. And then because the 2 classes in this components have to be 2, and then you have samples. Each sample will be assigned in different proportion of these 2 components. And some of these samples have a major components from a meta gene class 1, and then here is meta gene class 2. Basically, you just use 2 clusters of the major meta gene groups to explain the original matrix. And then since then, this method has been extremely popular in biology research field. And you can see the recent review paper, Enter the Matrix. Okay, so the senior author just lay out all the possibilities using NMF in biology research to in genomics. Genomics becomes a big data science, and you get different kinds of matrices. There are other review papers, applications, toolbox, applications to identify gene expression programs. So the whole idea has been summarized in this review paper. Okay, you can have a matrix observed. You can use PCA-SA or NMF. Especially you have dependent signals and non-negative values in your matrix. You decompose them into, it's called amplitude matrix and pattern matrix. Well, there's just different names. You can see, okay, amplitude is the relative proportion of the factors or components in each sample. I don't know whether this is a good name or whatever. It's describe the gene and use some kind of feature. Maybe you should call it, I don't know. Okay, whatever you call it, you have your abstract concept. How are you going to describe your decomposed matrices? Here, authors decide to use amplitude to generalize. So there are some kind of factors so you can assign values to it and give you the amplitude of the strength or how strong the signal is. And then you have pattern. That pattern is different proportion of those factors in different samples. And then people start to use this factorization, and here it's called computational deconvolution, but it is decomposition method. Okay, So here the application is you have input data, its matrix contains the measured expression of level from a heterogeneous samples. So it's a mixture of different cell types, and so you want to learn for both healthy and this cancer tissue and the different components in each sample, and this compare their patterns or their components learned from the original data, rather than directly compare the two observed matrices directly. And in 2015, and the people start to think about the decompose of the tissue measurement of gene expression into single cell type level. Because majority of, at that time, you have RNA-seq, you have a microarray, you get no single cell data yet. Okay, remember, you have a small scale experiment, you can do single cell, but in general, you have a matrix of gene expression. It's a mixture sample with different cell types contribute differently in each group. So you have a bulk sample and this mixture of different cell types with a different proportion, and they get you the overall readout. And the CyberSort is the first package. Try to learn from there and to decompose and to tell you in that sample and how many different cell types contribute how much for the mixture of the signal. And then in 2016, single cell data become available in the small scale, I believe, at that time. So you can add that components as a dictionary to read in and the support library to extend the CyberSort functionality to be able to use the single cell RNA-seq data to get different cell types expression components. Okay, so that's an example, and they have different cell types and with marker genes. So they know how to learn from the how to combine. Basically, you have educated guess about the components, and then to be able to assign cells into expression into the the mixture the expression value into the different cell types. Then there's a new method called music, and they say, okay, it's improved the previous existing method, not based on the pre-selected cell types. It will learn from the data itself, and the previous method also ignores cross-subject heterogeneous. Okay, so you just assume everybody have shared the common proportion of those combinations of cell types. But this method become more specified into learn the marker genes and also take into account of multiple samples and the heterogeneous in there into account. Well, NMF become even more important recently because of the introduction of the spatial transcriptome data. So what is spatial transcriptome data right now? So anyone heard about this spatial transcriptome? Okay, no. So that's a a new technology as an extension of the single cell RNA-seq. And basically you have your tissue section, and that's in the histological research, you have a tissue and make this cut into the small slide of tissue and put in a piece of glass that you can stain in different colors. But right now you can use these probes, and those probes, like 10x Genomics has its own solution. The probes has become an array, and each barcoded with a different 10x Genomics single cell barcode. So each probe have a different barcode. So you put your probe as a needle and into this section of the tissue section, and each probe assemble different location in the space. So you have a single cell label, barcode labels for that particular small amount of sample, and also because your array has been spatially arranged, so you have a spatial information about every probe you use. So at the end, you have a basically the single cell level or close to single cell level, depends on your probe, how many cells you penetrate on each time. And then because you have this spatial information, you can see, okay, at the end, you create this array, and this array reflects the original tissue and their position, different gene expression level. For example, this gene expressed or library size is higher in this sections of the probes, because you know the location, so you can reconstruct this map. Okay, so now the probe, for no matter how small you can design the probe is, you will never be able to touch all the time single cell, because this mixture complex tissue and also have the multiple layers. So you always penetrate multiple cells. You then end up with those data points. It's a mixture of maybe multiple cell types. So you need deconvolution or factorization to decompose it. Yeah,
you want the section, so you want to freeze it.
Yeah, you can do the fresh tissue and also some embedded tissue you can still use it.
I mean, you need to freeze the tissue.
You don't have to, but they do have a protocol for the freeze tissue. Yeah. Yeah. Okay, so this ST, spatial transcriptome, we will not cover in this lecture series, but it's getting very, very popular in the last 2 years. And many methods have been developed to see how can we analyze this type of data. Okay, so for this you have a single cell data and also have a spatial transcriptome data. You want to cross-validate sometimes, and you also want to see, okay, if you build the clusters from single cell data which are dissociated cell type cells, and how can you map them back to this spatial distribution of those single cell subtypes into the different location of the different patterns in the spatial information. Okay, in this case, people used a lot of this NMF idea to do the decomposition, to assign cell types for each location. So here you sample the cells for each location. Each location is a mixture of different cell type. Okay. You want to read them out and assign different proportion of different cell types for that particular probe you sampled. Then once you have those, you can reconstruct more accurately the spatial distribution of some cell type and particular marker genes expression, because you learned there whether this is a mixture of information, you decompose it and make it pure, and then you can specifically look at particular cell type and particular genes expression. Okay. This is a very new slide, and I think the method proposed yesterday and become published. And it's called Spice Mixed. And I got it from this Twitter, and the developer presented their results in a conference, maybe. You see here in the middle of this algorithm is an MF. I mean, you can see many of these tons of maybe overuse of this technology, this algorithm in all kinds of the similar research. Every day, there are many papers just pop up. We just cannot catch it up. But whatever you need is just to understand the principle here. Okay, you have all kinds of applications, all kinds of different constraints you can build in your program, but the key idea is the same. Can you recognize it here? Yeah. And MF, y is equal to x times m. So just different ways of interpretation. Okay, any questions for MF or general matrix decomposition? No? Okay. Okay, let's review what is eigenvector and eigenvalue. Well, the first, you have to have a squared matrix. Hey. Normally, your data matrix are not a squared matrix. What you can do? Normally, if you have a matrix X, it's a dimension of n and m, not a square matrix. If you have a non-squared matrix, can you use eigen decomposition? No, there's no way you can. Okay, because the definition of eigen decomposition is for squared matrix. But what you can do with non-squared, you have data. You can make it become a squared matrix by doing x transpose times x. Okay, so in this way, you get the covariance matrix, basically. Or you can do x times x transpose. Remember what this called? It's called gram matrix. So if you do this, you always make a squared matrix. Then you can use eigen decomposition. That you can search for eigenvalue and eigenvectors for them. Well, the covariance matrix tells you the correlation between your feature. If we think this M is features to express your to describe your N, the sample. Well, the gram matrix tells you the difference, the relative difference between samples. Okay. So one is between the feature variables, the correlation, and another is between distance between samples. So the definition of eigensystem is you have a squared matrix, then this square matrix multiply with eigenvector and this numerically equal to the eigenvalue times the same eigenvector. So let's go back here. The example is that you have a square matrix multiplied by this eigenvector, and the value is this, and then you eigenvalue times eigenvector is also that. All right. So numerically the same is the whole. So that's a set of eigenvalue and eigenvector for this squared matrix. And also, you know, before why the interpretation of that is, so you have this relationship, A is a squared matrix, but we have to look at A as an operator instead of a data. So this operator applied to a particular vector, okay? And it will not change the direction of this vector, but just rescaled, make this norm of this vector longer or shorter. Just the scaled factor, scaling factor of this lambda is eigenvalue, and x, this particular spatial vector, will not change the direction after you apply A and operator, is A's eigenvector. And the scaling factor lambda is eigenvalue. Okay, so that's the lecture 2 slide. I believe you should, I have a yellow star here. You always should remember this, and you can explain this in your language, and you can have the idea that treat the squared matrix as an operator rather than the data. Okay. So the eigenvalue and eigenvector reflect what the operator feature is, okay, as an operator or the rotator, right? Okay, so eigen decomposition is to decompose this squared matrix A into eigenvalue and eigenvectors product. So once you have the idea about this, and you know if you apply eigenvalue at eigenvector calculation, you get the V and lambda. You have this relationship. Now we are going to rearrange this to write A and put this to the right side, and then you have basically, if you V is a value, then you can have 1 over the V lambda in V. However, 1 over V is not the way to express this matrix of vector. So you have to write into as a inverse of that matrix, or inversion of the vector. Okay, so in this way, you put the way from the left side to the right side, and you actually decompose your original square matrix A into 3 parts, but the 3 parts, this way are the same, so only 2 in there. So that's what you at the end your expression looks like. Okay. Now people also found if your A is real and no imaginary numbers, is a real number in the matrix and also symmetric, then the outcome of this Q is multiple vectors in there. Those vectors will be orthogonal. What's happened? Okay, so this is just what I said. You have this relationship that you move this from left side to right side and rewrite this, and your V have to take inverse. So inverse V times this times lambda. Okay, lambda has to be put into a matrix because here is a vector or just single value. Maybe you have to put them this lambda 1, lambda 2 in the diagonal position, and all others are zero. So you put here to make this multiplication between matrices possible. So that's a Eigen decomposition. This Q is n by n squared matrix. Okay. All right. Any questions? Yeah. Yeah, the same. Okay, let's take 5 minutes break. Okay, let's continue and see what's the usefulness of Eigen decomposition. So, one thing is you can do to help you to compute matrix inversion using Eigen decomposition. So here we use this diagonal matrix in the middle of here to help you to compute the inversion of this. Okay. Normally it's difficult, but if you can decompose this, and your Q is fixed already, you know. So when you do the inverse, you inverse the Q, you flipped. So Q actually not change because your decomposition have a Q and a Q inversion. So you do the inversion of A and you still have the inversion of the Q, inversion of Q. All you have to change is in the middle of this diagonal matrix. So it's very easy to compute. It's just 1 over the value. And then you multiply it by, and you get the inversion of original A matrix. In this case, it's called matrix exponential computation. So you have exponential function. The A is in that factor there. So people found a rule that you can first decompose this into this P and two decomposed matrices and its inversion. Okay, so same formula, but in the middle you deal with this diagonal matrix, that eigenvalue diagonal matrix, and you do the exponential function for that matrix, and then you can easily get the solution after you multiply these two matrices back. Okay, it's a kind of shortcut if you can decompose a matrix into that two components plugged in the middle of the diagonal matrix for the eigenvalues. Then you can do the operation, whatever inversion or exponential for the middle of this diagonal matrix. It's very easy to compute because it's only single values in the diagonal. And then you can multiply the two matrix spike and get the solution for the original operation. We can try this using real data sets, maybe in the example in the computer lab. Okay, now we move to this most important matrix decomposition method. This applies to any matrix. It doesn't have to be squared, because if you have squared matrix, you have a lot of constraints, a lot of situation you cannot apply. But here is really important. So this film, and to show you the significance of this at early age when this method has been developed. Let me press this and play.
Relationships between the components of various kinds of systems. The system might be a bridge, an electrical circuit, a nuclear power reactor, or a sociological group. Each of the components of the system, the bridge struts, the resistors and capacitors, the neutrons, or the individual people, interact with the other components. The matrix elements represent the intensities of all these interactions. Analysis of the system using matrix techniques allows one to predict the effect of individual interactions on the overall system. Oscillations may be generated. Matrix analysis can describe the frequency and magnitude of such oscillations. This bridge, near Tacoma, Washington, was designed and built before the effect of such interactions could be completely analyzed. The wind has reinforced some undesirable oscillations with unfortunate results. Modern computers are particularly well suited to solving problems involving large matrices. The designer of the system can obtain accurate predictions about the reaction of his system to external forces. The computer is used to simplify the matrix so that most of the entries will be zeros. One method is known as the singular value decomposition. The original matrix is represented as the product of three matrices. In the second of these matrices, the only non-zero elements lie on the diagonal. These elements, the singular values of the matrix, determine the frequencies of oscillation of the original system. The other two matrices must preserve the properties of the original matrix, so they are orthogonal matrices. Each is the product of elementary matrices, which affect only two rows or columns. Scientists at Los Scientific Laboratory have been studying methods for the accurate and efficient calculation of the singular value decomposition and of describing to computer users how the computation is carried out. In this three-dimensional representation of a small matrix, each pyramid depicts the magnitude of a single matrix element. The diagonal of the matrix runs from the upper left to the lower right. Orthogonal transformations will be used to introduce zeros into the matrix. The initial transformations put zeros into the first row and then the first column. Each transformation affects two other columns or rows, shown here in blue. Later transformations introduce zeros into later rows and columns, while preserving the zeros already obtained. It is not possible to annihilate all the off-diagonal elements in a column, so this first stage produces a matrix with non-zero elements directly below the diagonal, as well as those on the diagonal. This film is produced by exposing a single frame each time a matrix element is altered. To illustrate roughly the computer time actually required for various phases of computation. The elements shown in red are involved in auxiliary calculations, which require time. Do not directly alter any elements. As more zeros are introduced, the rows and columns become shorter, and each transformation requires less time. The second stage of the calculation is a repetitive or iterative process, which reduces the size of the remaining off-diagonal elements, but does not zero them in a single step. During the process, new elements shown in red are temporarily introduced into the matrix. The calculations now being shown are primarily intended to reduce the size of the off-diagonal element at the lower right-hand corner. Once an off-diagonal element has reached a negligible magnitude, it is set to zero. The computation of the corresponding diagonal element is then complete, and the resulting singular value is shown in blue. During these iterations, most of the other off-diagonal elements are also being reduced in size, although not as rapidly. A few of them will occasionally increase in size. This makes theoretical analysis of the method difficult, but does not seriously impair its overall effectiveness. Since elements are being depicted according to logarithmic scale, the off-diagonal elements we see are actually quite small at this time. The transformations are still changing the diagonal elements, but the changes are not visible on this scale. Once a view of the singular values have been obtained, the off-diagonal elements have become so small that each of the remaining singular values is obtained with a single iteration. The final diagonal matrix, together with the two transforming matrices which produced it, then provide the basis for a complete analysis of the original matrix and the system which it models.
Yeah, by the way, Clover Moller is the creation of MATLAB language, and he's a professor and create the MathWorks, the company. And I think this is the early of this stage of the SVD developed an application and his MATLAB source code and been applied in this engineering work. Okay, so the one you see on the screen right now is this matrix here. Okay, it's a sigma in the middle of this two transformation matrix.
You have a hard time understanding your instructor. Do you wish there was a simpler way? I get it. It's frustrating. Go to class.
Okay, so this is very early age of the application. And on your screen, you have seen that singular values is inside this, in the middle of this signal matrix. So SVD, let me switch this for online students. So as I said, SVD can be applied to any matrix, any dimension and nullity. So in this case, I use example as a matrix of n by n. So we will decompose this into 3 matrices. And the first will be this U matrix. So we have A here, and the first one, U matrix, will be n by n. Okay, so I have U here. So n by n. And then we have multiplicate a sigma matrix, which is n by m. For the same length, okay. So the dimension of this and m. So that's my sigma. So you can do this multiplication, right? Because this n internally the same. At the end, you will get a matrix of what is the dimension of this product. N by m. So the product of this will be n by m. So here, the last matrix has to be n by m. That's a big. You actually transpose it. It doesn't matter because it's m by n. This will work, right? So that's the way the full solution of SVD will give you. If this square matrix U, square matrix V, and in the middle you connect this. So in the sigma, everything is 0 instead of this diagonal position. Okay, you have value of here. See, S1, S2, S3, until n. Stop by n here. The rest of them are 0. Okay, so that's the system we gave to you. Okay, so this here is a review paper for SVD and the related description of this discovery and history of development. So the system, this decomposition has been discovered over 100 years ago, okay? According to this review paper. It's mostly known and widely used So all matrices have a SVD, which makes more stable than other methods. Eigen decomposition only apply to a squared matrix. Okay. This is an example. If you have input matrix as A is not squared first, so this is 2 by 3. You decompose it into U, sigma, and V transpose. Okay, just as I said on the blackboard here, you have U is 2 by 2. This is 2 by 3 and 3 by 3. If you type in MATLAB and you do SVD, you get this solution. The solution, and in the movie we just saw, is emphasize the sigma matrix, and you have diagonal component values. It's sorted by descending order, and the first singular value is the largest, and then you have second in the diagonal line. And then U and V are called transforming matrix. Basically, it's rotate your system. Okay, remember you have a 2 by 2 matrices. You can consider this as a rotation matrix. And this 3 by 3 V transpose matrix can be considered as a 3-dimensional system to do the rotation. Well, in the middle is to do scaling. And why is it important? Because it can learn from your given data set to do the scaling, the direction, the most important direction, and also the scaling, the factors, the amplitude. Okay, so that's what I just draw on the whiteboard, blackboard here. A decomposes into here, and then you have this. All right. One second. So this is a very important topic. So I want to demonstrate using my examples to convince you that's the case. And you can decompose this A 1, 2, 3, 4, 5, 6. So this is just an example, right? And we are going to decompose into sigma B, use SVD. A. Well, that will give me 3 matrices. Okay. The value are the same as what you can see from here. Now, if I multiply them by, I get the original A matrix. Original matrix. Okay. Okay, so this is true. Okay, so now it's time to explain the meaning of this decomposition. And you know, this can be a rotation matrix. This is another rotation matrix because you know how to treat them as a rotation matrix. We explained before. We have the matrix. You can consider this a rotation matrix to rotate a vector, other data points, and sometimes depends on the diagonal values, whether you will rescale the magnitude of that. Okay, so now we treat this input matrix A as a combinations of two rotations and one scaling operation. So you consider this A, the first you do the rotation and then scaling and then rotation again. So here is apply in the reverse order. You apply the V as a rotation component. You rotate your two data points here as an example. You rotate them first. Then the value in the sigma and the scaling rescale the magnitude of your data point to no direction, no rotation, but rescale it. And then you do the rotation again using the U. So the whole operation A can be decomposed into three sections: two rotation, one stretching. So if you apply A to some of the data point blue and the red, at the end you will get the blue and the red in this rotated and stretched position. If you apply those reverse operation back, you can actually transform the data back to the original. So that's the interpretation, geometric interpretation of SVD. SVD decompose an input matrix into three components, and the two are doing rotation, and one is doing scaling. If you need a deeper illustration of this, and I think this is one of the best video you can watch. It's given by applied mathematician Nancy Cates, a professor in University of Washington, Seattle. So his video has been viewed so many times. Okay, he used 45 minutes to explain SVD. Okay, more detail. I hope. Okay, you can spend for 24 minutes to watch explanation for SVD. Okay, one of the example of SVD usefulness. So you see, we decompose a matrix from its main components. Okay, now it becomes not the rotation, but their meaning in this each element and values here. So you learned from the original input and decompose them into three matrices, and this gives you the strength of this concept. And here you have the concept of this the components similar. And this is not the most important because you can use NMF to achieve those, right? I think the most important one is so-called low rank approximation. back to this board here. Because our signal matrix contains those singular values indicate the strange factors for different direction. And because we already ordered, so this is the largest order, and this second, third. So I indicate those values by the bubble of size. You will see in many of those systems, this value decrease dramatically very quickly from a large value to a smaller value. And it may be just a couple of the jump. You have a large value here, smaller, and it's very close to zero very quickly. That tells you the contribution of other those components can be ignored. Okay, so what we can do with that is we can select, for example, only the top two components here. Well, I can ignore the rest of them. Okay, in this case, I reduce the dimensionality of this signal matrix from n by m into a 2 by 2. So I only use 2 by 2 matrix. So 2 by 2, very small. And to approximate the whole matrix, if I decide to use 2 by 2 here, then I have to cut this value into n by 2. Right, because I want to make this my application possible. So I will get rid of this part. Get rid of this part. 2 by 2. So now the end product of this is n by 2. And I have to do truncate of this part as well. It have to be 2 by n. 2 by n. Okay, in this case, I greatly reduce the dimensionality of the whole system. And this becomes approximation. You will realize numerically, you will reconstruct this, approximate very similar values here, even though you only use 2 components in there. It is much simpler, right? Okay, n by 2 times 2 by 2, n by 2 times m, n by n, same dimensionality of this, but you approximate that. So we use these sorted singular values and keep them to rebuild our matrix as our approximation. So this is called low rank approximation. Can anyone tell me what you can achieve use this low rank approximation? I can think that the first one, you can use much less information to represent your original data. So you're actually doing a compression of your information, right? You can you can save majority of the major pattern of signals using very small data set, compress it. And through this reconstruction, because once you have this component, you can reconstruct the original one. You actually denoise a lot of this unimportant signal here, only capture the majority patterns, major patterns in the data. So you can do compression of the information, you can do denoise. We have to think about other applications. Yeah, Alex.
So for the sigma matrix, you said it was sorted, right?
Yeah, it's sorted by the values here, the absolute values.
The highest values there.
Mm-hmm.
So it kind of captures the most significant information.
Yeah.
Okay. And then how is that sorted? Or is that part of the algorithm?
Yeah, it's part of Eigen algorithm inside. Always give you this sorting.
Okay.
So here I use example. I still have the system as you can reconstruct, but if I use only one component, I can recover some of this signal. Recover them, so you can reconstruct not using all, but use first two components, or just one component. You will still be able to recover some of this information. So we will try this in Search in Computer Lab. Okay. Okay, so that's the low rank approximation, and the P here, if you use just 2, and then this become 2 by 2, then this will become n by 2, and so it's the same as what I just showed you. Okay, so again, this is just a 2 by 2 sigma matrix. All right. So those illustration, I use only 2 components, and also this graph here also use example just 2 components. But of course, you can use 3, 4, 5, depends on your situation of your singular values in the sigma matrix. And you can also write them separately by adding up every component one by one. So in this case, we still have the matrix multiplied by another matrix by another matrix. You can rewrite in this way. Okay, this way is just a vector. So because this will become dimension as 1. So you write the first vector of the U, and the first value of sigma matrix is here is just single value, okay, not a matrix anymore. And multiplied by the row of the V matrix and plus the second components. So if you have more and you can add them up, you still recover original matrix. You can stop anywhere to get the majority information out, leave the so-called noise and ignore them. Ignore this noise. You can truncate anywhere in this form as well. Okay, so that's formula I just showed you in MATLAB. You just do this. Julia has its own package for matrix factorization, and all this method should be already in there as well. So how exactly internally this is computing? Okay, so we just show, okay, we can use built-in function to do this, but because this is so basic, and we know what we can use, how we can use, but internally, how this is computing. So the most contribution from the Stanford computer science professor, Gene Goldberg, and has done a lot of contribution. Source code is writing in Fortran. And internally, it's borrow this so-called QR decomposition to achieve. And also, you can achieve SVD using this approach. Okay, A is your input matrix. You can do the A transpose A, the internal inner product and outer product to get the covariance matrix, the ground matrix, and then to do two Eigen decomposition. And then you will get SVD solution. So that's where you can actually doing some, if you have special format of this, it's a symmetric, and there are different shortcut way you can use to compute that. So here is the explanation of this indirect method. So you do this multiplication in inner and outer multiplication of the matrix, and you get squared matrix, and you can do Eigen decomposition for them. So you can do Eigen decomposition. This matrix to get a U. Okay, so Eigen decomposition of this matrix help you to get a U, and Eigen decomposition for this matrix help you to get V. So you have all the U and the V, the sigma you can compute by afterwards. So as I said, you can use this to compress information to and also to denoise. In linear algebra, people use SVD to do so-called pseudo inversion. Okay, so basically any given matrix, you can decompose it first into USV, and then the inversion of that is applied to this in the middle of this signal matrix, and then you multiply U and V back, and you get the inversion of the input matrix X. If you cannot do this directly, you just decompose it to the inversion for the signal matrix and multiply it back and get the inversion of the original. So this is a P inversion, pseudo inversion. We remember we use the pseudo inversion because it's numerically stable. In many cases, you cannot compute inversion directly to the matrix, but you can use a pseudo inversion through this SVD and you get the solution. Okay, the finish of SVD again is most important one. If you have difficult to understand the essential review this lecture and also find external resource you can get and try to understand and find applications. So the last couple of minutes, I just quickly mention this ICA. ICA stands for Independent Component Analysis. Okay, so the meaning of this is separating a set of mixture signals into independent source. Okay, so here the keyword independent is important, so we want to identify independent sources to help you to decompose the mixture signal and find the independent sources. And widely applied for image analysis and signal processing tasks. The usefulness of the ICA can be explained by a ratio called cocktail party problem. So that if you are in a cocktail party and a lot of noise, you want to recognize the source of the noise. For example, there are a couple of people talk at the same time, and you receive a signal from a person A and a B, and you brain should be able to process this mixture signal and to recognize who's talking what. Basically, that's the idea. So in this example, you have a music as background and someone's talking, and then you have two microphones receive signals. These two microphones are placed in the different corner of the room, and one microphone is close to the background music, and another microphone is more close to the person that speaks. So you get the signal from the two sources, but because of the relative distance from the microphone to the two sources, and you receive the different strengths of signal and weighted by A1, A2, and for microphone A, you get a stronger signal from music, and and another from the voice. So you get a synthesized mixture signal, looks like that. From the voice of people, and you get, so for two is A from the background music, B from the person who speaks. And then the mixture signal looks like that. So for the ICA problem, you will receive the signal from these two sampled signals. Okay, both of them are mixed. What you want to do is to decompose this mixture signal into reconstruct original signal, one from the voice, one from the background music. Okay, so mathematically, ICA is to solve a linear algebra problem that you want to determine the values of this A matrix. A is a mixture matrix to tell you how the information, the signal you received is mixed from the source, and through this weight matrix, how they combine differently. So in our case, we have A1, A2, B1, B2 two sources, background, and the people speak, and also the weight differently. So you get from the two sources, you get the X, which is your sampled. So once we have this system, we want to solve the problem of the values of A. Once we have that, we will apply A to X. So X times A inverse should be S. So you reconstruct the signal from the source. Okay, so that's what we want to do here. There are many implementations and the applications of this algorithm. So here are some examples. The most famous is called the fast ICA algorithm. That's how internally this will be achieved. So you have a mixture signal as input, the mean and widening, and to steps, and then set the number of n. So this has to be determined, and then through this procedure you get at the end you extract the independent components. And this is the application, and from EEG, and so this is sampled from multiple channels, and try to decompose and get the source. And here you need to reconstruct that matrix and apply. So this is one of the applications in the EEG research lab. And that's whitening procedure, formula, and then that's estimation of we use this optimization procedure. Okay, so I have to, if you have time, maybe you want to go deeper and see what's the whitening here. Right, this whitening try to guarantee the source are independent at the end. For more applications and examples, you have reference of this. Okay, that's all I want to share today, and yeah, I'm ready for any questions for the last couple minutes before we end at noon. Okay. Questions? No? It's good. Okay. Then I will see you Thursday.